我之前都测过，
有限。对，然后这个大概像光缆上的部分，
你们前面
然后入口，而用的位置。
Okay.
那个我们
It looks like the volume on Zoom is working.
我想叫还有士力架，这不比香蕉好？
Okay, let's get started. Anybody have any questions before we start? Reminder, the proposal for your projects are due tonight. Yeah, tonight. Before midnight in the canvas. Any questions about that? Or anything else? Okay. Okay, so today we're gonna finish lead groups and related topics. So I'll just kind of review the where we ended last week. I'm trying to decide. Yeah, let's see. So let's just start with everything we did last week, basically. So we had a lead group definition. So a lead group is a group G, and group member needs with it has a binary operation, which we did with it's called multiplication. It's a group G that is also a smooth manifold. Such that group operations are smooth mappings. So taking two elements GH from your group as an ordered pair and mapping them to their multiplication of each other. This is a mapping from G cross G to G. That's smooth. Multiplication is a smooth mapping. And then the other thing we can do in groups is we can map a point G to its inverse element. Every point in our group has a unique inverse, G inverse. This is a mapping from the manifold G back to itself. And we need that to also be a smooth mapping. Okay, so if you have these properties 1 and 2, basically saying that all the algebra you can do with a group also are differentiable or smooth mappings if you think of them as manifold mappings. Okay, so that was the group, just a quick review. I'll skip over most of the other stuff we talked about, but just then skip to the end of last lecture on Thursday. We had introduced this concept of one parameter subgroups. So we have a group G, which I draw as a manifold because it's a Lie group, so it's both a manifold and a group. The special point we talked about is the identity element. Again, examples are like if you're in a vector space is a group under addition. The identity is the 0-point origin. If you're in a matrix group, like the general linear group, all invertible matrices, the identity is the identity matrix, and the group operation is matrix multiplication, inverse is matrix inverse. So anyway, we're at the identity of our group. We have a special tangent space that we're going to talk about more today, which I just at the very end sort of previewed, and this is called a Lie algebra. That's what we're talking about today. and also talking about group actions. But yeah, we're at this point, and we have a tangent vector, which we're using capital letters for, so I'll say capital X. Capital X is an element of the tangent space at identity, TEG, which remember is a Fractor G font in the notes, because I can't draw that on the blackboard, so I'll frequently write it this way, or try to write a different script, but I think this is more clear. So anyway, this is the tangent space identity. I have a vector. Now, one parameter subgroup is a smooth curve passing through the identity, right? Its velocity at the identity is x, let's say. It has some velocity through the identity, and to be a one parameter subgroup, the one parameter part just means it is curve. It's one parameter, like all curves. It's a curve. Let me write it as gamma. So it has a one parameter, a real number, and it's a subgroup, which means that if we only take points on this curve gamma, just consider the points that live on this curve, they themselves form a group. Okay, under the same operation, binary operation as the parent supergroup, if you will, capital G. Okay, to be a little bit more careful, we had this principle of homomorphism. What we said is that this homomorphism, you can define homomorphisms between two groups in general, but in our case with a one parameter subgroup, we say this is a homomorphism, this gamma mapping, the curve, its function itself is a homomorphism between groups. And so the group on the inputs are the real numbers under just real number addition, that's a group. And the group on the output is the capital G, your lead group that your one parameter subgroup is in. And so what that means, the homomorphism property, is that if I do the group operation on the input group, and there again, it's just taking the parameter of the curve and adding 2 points in the input to the curve, then that's equivalent to doing the group operation on the outside, if you will, on the G of the outputs. We can either do the group operation on the inputs or on the outputs. And then the other rule about homomorphisms is that at the identity, the identity in the real numbers is 0. That is going to equal the identity in your output group, G. So this identity element is exactly where gamma of 0 lies. Okay? And we said that these are the 2 rules you need for homomorphism. If you put these 2 together, you made S and minus S, you get gamma of S is equal to gamma of S inverse. So there's a kind of a thing you can derive from this very easily, that gamma of S inverse is the same thing as gamma of minus S. Okay, so the inverse, if you're at some point, you go out to time S on the curve, and you want to invert that point in the group G under the group multiplication, then you just go the opposite direction, minus S along the curve, away from 0 in the opposite direction. And you'll get the inverse in the larger supergroup here. Okay, so that was the one parameter subgroups. Notice this mapping is defined for all R, because you have to take the whole group of real numbers under addition. So you can go from minus infinity to infinity in the parameter, and this all this algebra still works, the homomorphism still works. Okay, and just to give some examples, give a couple of examples, because we sort of, sorry, I'm just going to make sure I can see my video so I know if I lose the camera. Just we sort of concrete examples here of some groups and their one parameter subgroups. Let's take our group RD, D-dimensional Euclidean space. The one parameter subgroups are going to look like gamma of T equals T times X. Okay. So let's think about, X, same thing here. X is a point, sort of vector, I should say, in the tangent space at 0. Remember, the identity element of the vector space is the 0 vector. So if I look at this, let's look at a R2 kind of drawing. If I'm at 0, the 0 vector here, the origin, that's my identity, that's E. It's a little bit confusing because we're used to E being Euler's number from exponential, but identity element is the 0 vector. A tangent vector at the identity is just a vector which is anchored at 0. I can think of TEG, the tangent space, is really equivalent for all intents and purposes to the same space RD. That's the tangent space is the same space basically, or you can think of it as another copy of RD, if you will. The tangent space at identity is just RD also, so X is a vector, a d-dimensional vector. And now gamma of T says the one parameter subgroup with this velocity is just the ray, kind of infinite line, if you will, that moves at velocity x as you change parameter t. So it's just a straight line. Okay, so that's easy. And of course, a straight line, no matter what directions it's going in, no matter how fast you transverse, you think of the velocity here, right? D gamma dt is equal to x, right? That's pretty straightforward. That's velocity anywhere, but we care about the velocity, specifying velocity of the identity. So this is pretty easy. And the straight line, of course, we can think of as homeomorphic to the real line. It's just a one-dimensional line. It just happens to be, embedded into RD in a particular way, in a particular direction velocity. Okay. So that's an easy example to dispense of. But any questions there? Yeah.
The tangent square of G is equal to the dimension of dr. Is that
This line, I mean?
I know. I mean, what is you mean that they're the same thing?
Yeah, this means equivalent to as a space. It's technically not G and TEG are two different spaces, right? Like a skier, for example, and its tangent space are not the same space. It's technically the case that our manifold is not the same as the tangent space at a point, but it is the same type of vector space, the same vector space, a d-dimensional real vector space. So I wouldn't think of it as like there is a second copy of RD. Okay, so you've got the points in RD are the points in G here, and then the vectors in TEG are, think of them as vectors anchored at 0 kind of thing. So those are tangent vectors. So they're kind of two separate things, but they're the same space, equivalent spaces. Okay, so that's example number 1. Let me see. Let me do kind of the general example here for matrices. Let's think of G. Let's actually before I get to matrices. I did this example last time. Yeah, but I don't have to erase it because I haven't actually said it yet. The G are the real numbers greater than 0 under multiplication. Okay, we already said when we talk about just general homomorphisms, we already saw the homomorphism that to go from addition, which is what the gamma starts on the left, the parameter coming in to the left is addition, group of real numbers under addition, to then change addition to multiplication, we use the exponential function. Okay, so this is the homomorphism we talked about last time, and this is a one parameter subgroup. And of course, the output group is also just one dimensional. But this is an example because this will be interesting later. And I'll explain here for a second here that this at gamma of 0, you're at 1. The identity on the multiplication is 1, of course. I'll write that out explicitly. So this is the identity of real numbers under multiplication. Here, the derivative I'll write it out, d gamma dt is also, or I need to be careful, at 0 is also 1. So the tangent vector, if I think of G is the real line, this is 0, and I go out to infinity. Zero's kind of a hole there, it's not included, it's everything greater than 0. Okay, the identity is equal to 1. And now I can put a tangent vector here. The tangent space here is anchored at 1. The tangent space is, for all intents and purposes, as a vector space, just the real line under addition as vector space, right? So this is the vector space, it's just the real line sort of attached here at 1 is the tangent space. And I can talk about tangent vectors. So I have this velocity equal to 1, and that gives me the exponential function as 1 Cramer subgroups. And then, of course, exponential will go out to infinity, or it'll asymptotically kind of approach 0, but slow down asymptotically. Like if I flip this axis up this way and plot the exponential function, we know how we get something like this. So this is this axis, this is G, this is G. And this is kind of writing gamma, if you will, as a graph. Okay. But yeah, so this is the point I want to make, is that I can change the velocity at identity. So this is velocity equal to 1, but I could just kind of make a different velocity, just give it some real number, alpha, and alpha can be a positive number or it can be a negative number, depending on which way you want to go. And if I do that, I really just need to put an alpha into my inside here, and alpha is just any real number. And by real number, I mean it's a point in the tangent space of the identity. Okay, and now my velocity at 0, at t equals 0, which is at the identity in G, is equal to alpha. So I can specify the velocity as to be whatever you want in tangent space by making this scale factor. Okay. Any questions there? I could have called alpha, by the way. Maybe if I want to keep it with my notation, I could call alpha just capital X, just to keep with the same notation. Maybe is it's kind of weird to call a real number a capital X here, but that is just a real number, and I can think of it as the capital X kind of coincides with my tangent vector notation for Lie groups here. So maybe I should have done that. But the same thing applies, is that I just need to scale my parameter t by that tangent vector value in the exponential function, and now I've got my 1 parameter subgroup with any velocity you want in the tangent space. Okay. Any questions? So one thing I mentioned last time, and now these examples make it a little more concrete, is that at the identity, you've got this tangent space. I can pick any tangent vector you want, any x, okay? And there's there exists a 1 parameter subgroup with that initial velocity. It's a one-to-one mapping. Any tangent vector has a unique 1 parameter subgroup, and any 1 parameter subgroup has a obviously has a unique velocity at identity. And so you can kind of see that in these two examples. Any vector x I pick, clearly I can set up this construction. Any real number, any vector, tangent vector I pick here, this is well defined and gives me a unique 1 parameter subgroup here. Okay, yeah.
And just clarifying, is X both the tangent vector and the velocity?
Yeah, but so remember, one way to think of tangent vectors are they are velocities of curves. So yeah, exactly. Yeah, that's correct. That your statement is correct. That the capital X's here are tangent vectors, and we're also thinking of them as velocities of this 1 parameter subgroup curve at time equals 0. That's right. The other thing we talked about last week, which I will not spend too much time, but I'll just mention without writing down a bunch of stuff, is that we talked about this concept of left translation or left multiplication by an element on the left, or you could also do the right. And that left multiplication the derivative of that mapping can map your tangent vector to any other point. So if I take here, when we say left multiplication, we just mean addition. Left multiplication of x, the derivative of addition is just 0. And so I get just x is the left multiplied. So I get a vector field everywhere, which looks like just like copies of this x vector just translated to different base points. And the point is that if I do this left multiplication derivative, then the velocities will kind of be the velocities of the curve anywhere on the curve. Obviously, the velocities up here I don't care about because they're not on the curve, but on the curve, I take x and I just move it to some other point on the curve. Otherwise, just kind of slide it along, and that's still the velocity. Here for the exponential function, left multiplication by a group element is actually going to be, this is if I go to a different t, right? If I evaluate this at a different t, let's say at s, then at gamma of s, I take dt of gamma, I evaluate it at some parameter s. I'm going to get not just x, that's at 0. I'm going to get with the multiplication rule, I get another exponential of sx here. Okay, so and here it's commutative, multiplication is commutative. So this would be left multiplication, right multiplication is the same thing. But the point is that if you want to take this velocity at a different point, then the identity, you move it here, let's say you have to do a left multiplication. This is technically the derivative of left multiplication or right multiplication. I move it to a different point. So the velocity scales exponentially, and it's really just the velocity of this exponential function. That's all we're doing here. Okay. So these one parameter subgroups, their velocities are specified at the identity, but then that fully specifies the curve. And it fully specifies obviously the derivatives of the curve, but the derivatives of the curve have this nice algebraic relationship that they're just the derivative of multiplication, of the Lie group multiplication, to take this velocity to any other point on the curve. Okay, now these are very simple examples. The more interesting examples are when we get to matrices, and of course I have to go back to the eraser. Sorry, for people on Zoom, the board is oscillating here. So let's do one more example with matrices. Actually, two more examples. I'm going to do for non-singular matrices, GLN, on how that looks. Sorry, board again, lost me. We'll see how that looks for subgroups is just like the rotation group. So let's take G equals, again, GL, I'll call it D, G, and D, D-dimensional, D by D matrices. Okay, this board, the camera is very sensitive when I'm standing over here. I don't know what that's about. And if I keep moving, it will keep the board over here. So GL of D is D by D matrix. Okay, that's ridiculous. I might need to do, sorry, I'm gonna stop, wait, no. I start cursing, it's because of the camera, not you. So I'm gonna actually try to control camera myself. This might be a disaster, but try to keep it just to stay over here. Good. Now it won't move. That was not off screen. I was right here on screen. I was watching myself, and it went away for some unexplainable reason. Okay. Right, so D by D matrices that are non-singular, they have non-zero determinants, so you can take inverses of them, and all the group operations are valid. The group rules are valid, right? In this case, one parameter subgroups. Oh yeah, first let's talk about the tangent space. So the tangent space at identity of GLD is the notation is this is again is the fracture font typically, but I can't really write it. But think of that weird like old German font G and L of D. And what this is, I'll just say in kind of words, are all D by D matrices. All really, I should say, all real value D by D matrices. So that's all real D by D matrices. Okay, so now you can have things that are singular matrices. So now the singularity of the matrix is here that you can only have non-singular matrices. Here you can have any old matrix you want. And what's the picture here? GLD, if I think of the vector space of all D by D matrices, okay, there's the zero matrix. That's obviously singular. Okay. And if I take all matrices where let's say I'm gonna say all, you know, the condition for A to be a GLD is that determinant of A is not equal to 0. Okay. And we talked about this a long time ago, or maybe just last week, I can't remember, but this constraint, right, not equal to 0 constraint means that you're in an open subset. And so I'm just going to kind of draw something that looks like this. This is GL of D here, and actually maybe I should yeah, be very careful, because remember there are positive determinant and negative determinant matrices. I need to draw, okay, the gap here should really just be kind of like it's a lower dimensional subset. The determinant equal to 0 is this boundary between either positive determinant matrices and negative determinant matrices. And both of these subsets are in GLD. They're separated by the determinant equal to 0 matrices, but that's a lower dimensional subset. It's a one dimension lower, right? Because you have one dimension of constraint determinant equals 0. That gives me a kind of so if I have a D squared dimensional space here, this is a D squared minus 1 dimensional space, and then another D squared dimensional space on the other side of it. But they're blocked from each other. You can't go from this side to this side without passing through the 0 determinant matrices because it's a continuous function. Okay. So yeah, so you have this picture. Here's GLD. The identity matrix. So that's our identity for the group. E is the identity matrix. I'll draw as right as the usual capital I for identity, D by D identity matrix. That's the identity matrix. Because this is an open subset, which is also the same dimension, D squared, right? The tangent space, GLD, is all D squared, make the vector space of all D squared matrices. And remember, as a vector space, it's really the same thing as all that's RD squared. It's just a D squared dimensional real value vector space. So that's really what the tangent space is in GLD. Okay. So again, you can kind of think of that copy of, because it's just an open subset of a vector space, a copy of that vector space is the tangent space there. Okay. And what does this mean? It means that, I mean, if I think that intuitively, vectors here, you can always think of a vector as like just an infinitesimal perturbation of a point. And so if I take the identity matrix, and any infinitesimal perturbation of the identity matrix is still non-singular. And it doesn't matter if I move in a dimension, which is a singular matrix itself, the tangent vector, the perturbation can be one of these singular matrices, because I'm in an open ball, I can move in any direction, at least by some small epsilon, and I'm still non-singular. Okay, so that's kind of the intuition of what's going on there in that space. And really, if I again move this this tangent space to some other point, if that still holds, I'm just doing again to get from the identity to some other tangent space, I can do left multiplication derivative, and any tangent vector again is any any matrix at all can be added at least infinitesimally to any point. Now, of course, as closer you get to this boundary, the smaller of a perturbation you might need to take to stay in this open set, but there's still an epsilon ball, because it's an open set, there's an epsilon ball. Any direction I go, I'm still non-singular. Okay? Any questions about the tangent space there and just kind of the general picture? Yeah, so then, so that's our setup. Let's again talk about one parameter subgroups. So gamma of T, it turns out we can write this down. So what is the homomorphism here? It is also the exponential of X, but now of course, when I say exponential, we're dealing with matrices. X is a matrix. It's a matrix it's a D by D matrix. And so exponential is what's called a matrix exponential. Okay. It's very easy to at least explain. It's hard to compute maybe, but easy to explain what is the matrix exponential. It's just take the usual Taylor series of the exponential function, and instead of putting little x as the value of the Taylor series, put in the matrix as the value of the Taylor series. So let me just write down what exponential of capital X would be, and you can put the T in. Also, it's just easier to write if I just say, so I have a D by D matrix X, and this is the matrix exponential, and yes, it is overloaded notation because it's the same notation I'm using there. It's the identity matrix plus X squared over 2 factorial, which yes, is just 2, but the Taylor series just to emphasize X cubed over 3 factorial, et cetera, et cetera. Okay, and if you've seen the Taylor series for exponential real value functions, which hopefully everyone has at some point in your life, you can probably remember or remind yourself that that's just 1 plus X squared over 2 factorial, X cubed over 3 factorial, and keep going to infinity. All right, in fact, let's do that. It's the sum for k equals 0 to infinity of x to the k over k factorial. Okay, and of course, x to the 0 is the identity matrix. So that's where we got the 0 there, identity. Okay, so yeah, so this is a well-defined Taylor series that converges, and it gives you the matrix exponential, much like we had the real valued exponential that we're used to. If I put a t in here, I just hit t times x in parentheses to the k power. So you have a tx, a t squared, x squared, a t cubed, x cubed, etc. So the t is just the scale factors, just scale to x, that's fine. Okay, so it turns out the one parameter subgroup is just like for real numbers under multiplication. And if you think about it, real numbers are just a special case of GL1 equals 1 is just real positive real numbers. Or I should say non-zero real numbers or non-singular 1-by-1 matrices. So this example number 3 actually is a kind of a generalization of example number 2. And the one parameter subgroup looks very similar, obviously. And I'll just make the point that d gamma dt, which I'll get that a little bit, at 0. If you take the derivative of this thing, it acts just like you would expect. It acts just like the real valued exponential. This will just give you capital X as the derivative of this gamma of t. And it's really just the derivative with respect to take the derivative with respect to t. You get a chain rule, right? That this X matrix goes outside, and if you evaluate t equals 0, this is identity. Exponential of 0 is identity. Okay. So any questions there? All right, so this is a little bit tricky to get your mind around. Obviously, if it's just a number and it's scale like a scaling, you can kind of see, okay, the one parameter subgroup just changes exponentially, but what's a general matrix and it's exponential, it's not so easy to get your head around. So I think it helps to go to another example, and I have to move the camera. A subgroup of GLD, which we're used to working with, is this rotation group. If we come across multiple times in class. So now example number 4, G is, oops, sorry, that's what we just did. FOD, D-dimensional rotations, or typically, special orthogonal group, typically we have D equals 2 or 3 in most applications. So that's what we're talking about. There are applications for other dimensions of D. We'll actually talk about one in a minute. This is a subgroup of GLD. That's what this little triangle notation means, is it's a subgroup. And again, maybe I can leave off this equality. It's not less than or equal, it's just strictly a subgroup that's smaller than GLD. So yeah, the rotation matrices. They have the exact same one parameter subgroups. Actually, before I do that, let's talk about the tangent space. So the tangent space to the special orthogonal group at the identity is called, again, this stupid font I can't draw. Try maybe like some curlicue, SO, little so in Fraktur font, D. It is equal to all skew symmetric matrices. Let me say all D by D skew symmetric matrices. Which I think we've covered this fact before, but this is important. So all D by D skew symmetric matrices, that means that if X is in the tangent space at identity, it's a D by D matrix such that X equals negative its own transpose. Okay, and if I were to write it, you'd always have zeros on the diagonal, because if you take the transpose, the diagonal elements stay put, so they have to be the same. But any element you have over here, like if I have, let's say up here, X ij, and if I flip down here to the transpose thing, I get X ij minus. So you just have whatever you have up here, you transpose it, you get the negative of that on the other side. Okay. Couple of examples that we're used to, SO2, two-dimensional rotations. And again, let me make this this is the tangent space. So an X in SO2 means that X is equal to something that looks like the following. I'm going to say minus theta here. Oops. Bracket. So there's only one element, one degree of freedom here. It's the one off diagonal element, because when I transpose it has to be just negated. So you have something like this. Now the matrix exponential is still the one parameter subgroups. Okay, through the if I take this two-dimensional matrix, 2 by 2 matrix, I should say, and exponentiate it, I get the one parameter subgroup. And if you do that, actually, let me make this actually a little bit even more simplistic. Let's just make this minus 1, 1. I'll just see in a minute why I'm doing that. If I do that for this particular X, I do this matrix exponential, and you can kind of verify this. It simplifies to the following. Okay, so you exponentiate this matrix scale by t, and you get the usual form of a rotation matrix by t, a 2 by 2 rotation by t. Okay, so you see the I can think of SO2 as being a circle. That's all SO2 is just a circle And, this is an angle of 0, and then t just goes around the circle as cosine t sine t. And that's really the only, it's a one-dimensional group, it's a circle, so that's the only, kind of the only, one parameter subgroup is just to wrap around the circle as rotation by t. Okay, now, of course, I could have made x, I could have left that theta in there, and this would be t times theta, so you can move at a different velocity around the circle and go negative around the circle or positive around the circle. But the point is that exponentiation of the matrix gives you just rotation by constant speed around the circle. Okay, so that's the one parameter subgroup that we get here. Any questions there? All right, moving over again. The last thing I'll say, and I think this is in the, maybe in the notes, I think I do SO3 as well in the notes. SO3, if I just go d up one dimension, I take a tangent vector. Sorry, my fracture font drawing is kind of ridiculous. So little SO3 is the tangent space. This is all, again, d by d skew symmetric matrices. So now X is going to have to look like the following. The 3 by 3 matrix, and I'll write it in the following form. I'll say, make sure I get this right. Vy minus Vy minus Vz, Vz minus Vx, Vx. Okay, and I might have this off by a minus sign. I always get this backwards, but this is roughly correct. Modulo possible minus sign here. So Vxyz. I think I did this wrong. Sorry. I did multiple blocks wrong, but let me this is y. It doesn't matter that much. You kind of get, you can get the point of what I'm trying to do here. But this is y. This was z. That was correct. I didn't have it wrong. Anyway, I think I had seen y backwards. So yeah. So what we're doing here is we're defining really 3 values: v, x, y, z. I can just write this parameterized just a 3 vector vx, vy, vz. And so we can see that this is really equivalent to R3, because any x, y, z values are valid skew symmetric matrices, right? Same thing over here. I could see that little SO2, the tangent space is really just R1. There's just one number parameter. Okay, and what does this x give you if I again do the one parameter subgroup in that direction, that velocity, if you will, starting at the identity matrix, the identity rotation, rotate. It's a rotation about this axis in 3D. So if you think of V is a vector in 3 dimensions, so think of just a vector point in 3 dimensions. And what I'm going to do is I'm going to rotate around that axis of rotation. So any 3D rotation actually is keeping, this is anchored at 0, keeping one dimension fixed. One dimension doesn't change, and then the 2 dimensions sort of orthogonal to that axis get rotated like a 2-dimensional rotation. That's basically any 3D rotation. I can pick an axis and rotate around that axis. That axis stays fixed. Okay, so V is the direction of rotation, the axis of rotation. but the amount of rotation you do around the theta that you're rotating amount of I is the norm. So if I call that theta, the amount I've rotated around this axis, that is the norm or length of V. Okay, so I can pick a direction of rotation and pick how much I want to rotate about that axis by specifying some vector V. That gives me both the axis and the angle, all kind of in the same vector representation. Yeah, so the point is that if I do this at t equals 1, I just do exponential x. If I just did exponential of x, I get this rotation I just mentioned, which is that take the axis v and rotate by theta. Now, if I keep the t in there, then I'm just scaling the norm by t. So then my axis of rotation is t times the norm of v. Okay, so but that's what the one parameter subgroup does is you're keeping this axis fixed, and as t changes, you're just rotating by, again, a constant velocity, angular velocity around this axis. Okay, so that's and you can see why this is a subgroup, right? Because rotations about a fixed axis are really equivalent to S of 2. So they're really a subgroup of 3D rotations. It's just a 2D rotation subgroup, if you will. I mean, equivalent to that algebraically. Okay, so yeah, so that's the last example of one parameter subgroups I think I'm going to do. Any questions? Okay, right. Yeah, let me stay over here to avoid board gyrations again. And we'll move on to the algebras. So this TEG is what we call a Lie algebra. And a Lie algebra is a vector space. And we know in the case of our Lie group tangent space, of course, it has to be a vector space because it's manifold tangent space. They're always vector spaces, but it's got an algebraic structure to it that most vector spaces don't have. So it has a binary operation called a Lie bracket. It comes with this thing called a Lie bracket. I can take two tangent vectors, two elements in my Lie algebra, and multiply them together with this bracket operation. This will give me another tangent vector. Whoops, yeah, TEG. And this is defined, you know, again, like always for all x, y, and TEG. And it satisfies such that the following properties hold. I have to have anti-commutativity. So if you flip the order of x and y, oops, I kept it the same, then you negate the answer. So xy equals minus yx. It's bilinear. I should put that first, maybe. Bilinear means that, right, if I have an ax plus by z, right, that just breaks down to ax z plus b yz. So that's linear in the first element. I could do the same thing on the other side, and it's still linear to the other side too. So bilinearity is one thing. And then the last one, which is the tricky one, is called the Jacobi identity. And this is if I take three vectors and I take the bracket of two of them and then do another one with the third one there. And now what I'm going to do is I'm going to just cycle the order x, y, z's are in and add them all up. So I'm going to cycle, and the cycling kind of wraps around here, x, y, that, and then finally cycle to y, dx. You cycle all these things like so, and that always will add up to 0. Okay. These are the axioms, again, that the Lie bracket has to satisfy. Okay, now this, I don't need a Lie group to define what's a Lie algebra. I can just say any vector space that has a bracket operation that satisfies these rules, I can call that a Lie algebra. It happens that any Lie group you have, its tangent space identity, this very special tangent space, has a bracket operation that will give you these algebraic properties. And we'll explain kind of where that comes from next. That's kind of the idea. Okay. Right now, these are kind of esoteric, just kind of, again, rules, these axioms you have to satisfy. Don't worry about if they make sense or not right now, because we're going to just show what is this bracket operation for Lie groups, specifically their tangent space and identity. And then we'll see why is it useful. And you're going to use this in the homework you're doing. Oh, good. Is that a piece of chalk? Okay. I was running into a very little small nub of chalk. Okay. So I would say, is there any questions about this? But I don't want to take questions because don't worry about understanding it at this point. We'll try to make it more relevant here in a minute. So let me give an example that will kind of, I have 2 examples that will kind of give us some motivation why we care about this Lie bracket operation. So the first example is as follows. Let's think of, I've got images, like this is kind of relevant to your homework. I've got images, and what I want to do with these images is I want to translate them, and I want to rotate them. So just 2D rotations and 2D translations. Okay, so let's say I've got an image of face. Okay, and I'm going to put a nose on the face because I need a center of rotation. So let's say that's the middle of the image. I'm going to rotate about the origin. The center of rotation that stays fixed is going to be the nose point here. Okay, I can rotate this image, I'll say by a rotation matrix, that same kind of cosine sine 2D rotation matrix. I can apply that to this image and rotate it, right? By some amount. Okay. Let me make a box here so it's clear that, it's kind of still in the center here. Okay. Another thing I can do is I can translate this image. So let's say I've got some translation vector t. I'm just going to translate along the x-axis here. Actually, t is a bad letter to use. Let me use v just for not making things my frame or my curve. So let's just say that made the head move from the old center where the nose was over a few pixels to the right. Okay. Now let's think of this. I take this rotation, and now I'm going to apply the translation, same translation. Actually, let me do it a little bit. This is going to look a little bit strange, but bear with me. I'm going to do it over here. Okay. What if I translate the rotated image, right? I'll get the face will look like that. Everybody agree? So I'm just applying this V translation. Now let's take the same rotation here to this image. What am I going to get? Anybody tell me? Am I going to get this image? Rotate by the thing. Let's see, whatever that is, let's say 45 clockwise rotation, let's call it. What would I get? Yeah.
Like right bottom corner.
Yeah, exactly. This is gonna still have the same center of rotation, the origin of the image. And so this whole head, you can think of like the vector V, which went from the original center of the image to the current new point of the nose. I'm rotating that whole vector. The whole head is coming with me. And so this head is going to be down here, the bottom right corner of the image. A little bit tricky to draw, but you get the idea, something like this. So the orientation of the head will still be the same 45-degree kind of tilt, if you will. But now the position of the head is not at V, it's at RV. Oops, I should do it here. This vector from the original origin to the nose is R times V, rotated V vector, translation vector. Okay, so the point here is that rotating an image and then translating it by the same things, it's not the same as translating it and then rotating it. Rotation and translation don't commute when we're thinking of them as being applied to objects in the physical world or into images, pictures that we might want to transform. Okay, and why is this the case? Well, the group we're working with when we do rotations and translations in 2D, I'll just say for now, is SO2 semi-direct product. This is something we haven't talked about before. R2, so this is the rotation group, this is the translation group, and this semi-direct product, what it means is that if I have G1, equals a rotation and a translation R1V1, and then G2 is R2V2, then multiplying G2 times G1, and I'm going to think of this as you apply it on the left of a vector, so like I do RV is to the R is to the left of the vector, right? So I apply the G1 transformation first, and then I apply the G2 transformation second to the image. If I multiply these two together, I'm going to get R2 times R1 for the rotations. That's all fine and good. And then I'm going to get, let's see, make sure I do this right. I get a V2 plus R1, whoops, R2, sorry, R2 and V1. Okay, so 2D rotations commute. If I rotate by just a theta and then another type of theta, I can do those in any order. 2D translations commute, but if you combine rotations and translations jointly, they don't commute anymore. And this is why, because when you apply the first V1 translation, and then you rotate by the second transformation, it's going to rotate the vector that you translated by also. Okay, obviously, if I switch G1 and G2 in different orders, R1, R2, that's okay, they can commute. But now I'm going to get the R1 applying to V2, that those indices flip and I don't get the same, this won't be the same vector. Okay, so that's what's going on with anti-commutative or non-commutativity, I should call it, of the, this is called like a rigid body transformations, the special Euclidean group. This is called special Euclidean group in 2D. So special Euclidean because it keeps the Euclidean geometry the same. Yeah, and so this is not a commutative group, even though it's built from two commutative groups. But then how do we actually see this we can actually see this and how it affects just from the tangent space. You don't actually need the whole group to know that this is a non-commutative group. We can look at the lack of commutativity and what it looks like infinitesimally in the tangent space. And that's what the Lie bracket actually is going to tell us, is this lack of commutativity. Okay. I probably won't have time to go through the Lie algebra completely here in the next 15 minutes. The other example I want to give, and I'm just going to leave it as a maybe the Lie bracket is there. I'll move to the other board. Okay. This is my favorite example of non-commutativity and the importance of Lie algebras in the world. Is the parallel parking example, and I don't know if anyone has read the notes or had a chance to look at the notes. This is optional notes to look at. You don't need to know this, but if you want to impress your friends about your knowledge of Lie algebras, this is, I think, a fun example everyone can relate to. The parallel parking. If I have a street. And I'm drawing cars as boxes. This is the curve, let's say. We're looking at a car, like a street from above. And I come along in my car. As a good parallel parker, I pass the spot. And now I want to back into this parking spot, right? Now, let's say my car is length L. And the parking spot from absolute tip to tail, if you will, of the cars in front and behind is L prime. Question, how big does L prime need to be for me to fit my car of length L? And let me make an assumption which you may or may not need. Let's say all cars have the same width W, like all these cars with width W. That may or may not matter. I will see in a minute. Well, how big does L prime need to be relative to L? Obviously, L prime can't be less than L, because no matter how you move your car, you can't fit into something less than L. But how big does L prime have to be? Anybody have a maybe not an exact formula or anything, but just a reasoning about this? Yeah.
Maybe some pi over 2 times W plus L.
Okay, and I think you're thinking, so I can rotate,
Yeah,
and so that the W fits in here as I rotate back, right? As I go pi over 2, it's gonna come in at a 45-degree angle. I think I'm following your logic.
yes, yeah.
Okay, that's a great, yes. Anybody else have anything different? So I think the argument there is that if I'm coming in at a 45-degree angle, I need to have my corners come in through there is kind of the thinking, right? Well, it turns out, I'll just give the answer. L prime is any number greater than L. You can have L plus 1 millimeter space, and you can fit your car into the parking spot. So next time you're driving and your friend is with you, or a loved one that and they're like, you'll never fit in that space. You're like, no, I've got at least 1 millimeter free. I can totally fit in that space. Any space that's bigger than your car, and it could be epsilon bigger, doesn't matter what epsilon is, you can parallel park into. Again, in theory. Now, your actual skills at parallel parking, have to be perfect sometimes to get that kind of parking, but in theory, you can do it. And the reason you can do it is because it's a Lie algebra with non-commutative operations. It's really very similar to this SO2 semi-direct product SO2 semi-direct product R2, this special Euclidean group. I won't obviously have time to do the full derivations. It gets into some gory, it's not like hard math, it's just like tedious. It's kind of like the Christoffel symbols you had to do. They weren't hard, they're just tedious, right? So but if you read the notes, which I really highly recommend because it is a really cool example. I can think of a car. This is sort of the front tires, back tires, and axles, right? This is the midpoint kind of the car. I can think of a car's configuration in space as parameterized by just the XY position of the center of the car. And then if I kind of have like some x-axis here, I have one other thing, which is the orientation. I'll call it phi. I think that's the word, whatever they use in notes. Phi is just the angle of the front back axis of the car. And that's 3-dimensional space. So sorry, there's a little gnat that's been flying around. I don't know if I smell that or something, but anyway, there's a 3-dimensional space, XY phi, of all possible configurations of where your car is in space. Now you have a little bit more, and so the controls you have are different from the configuration of where the car is. This is kind of a state space. The controls you have are the following: drive and turn. Right? I can only drive, and these are kind of like 2-directional things. I can drive forward or backwards, and I can turn left or right. Okay, so I can turn the front wheel axis really. Unless you have a funky car, you can only really turn your front wheels. And so the axis that you turn to is another control theta in that set of notes. And again, the drive is only a forward backwards. It's a one-dimensional kind of degree of freedom. The turn is a one-dimensional degree of freedom. So you really have 2 degrees of freedom to change a 3-dimensional state space. Okay. And what you need to do is you need to be oriented, parallel with all these other cars. And of course, you need your midpoint right there in the midpoint between the front and back of the 2 cars. And you need enough space L prime to be just slightly bigger, where slightly is any epsilon bigger than your car length. Now, why does that work? This is, we'll come back to that. Let me do Lie algebras here for a second. Because I need the Lie bracket to tell you why that works. I think I'm going to run out of time. I spent a lot of time on examples and which are good to be concrete, but it didn't take quite a lot of time because I only have 6 minutes. So let's really quickly talk about the Lie bracket and why it had something to do with the commutativity properties of your group. Okay, this will be the. I might need to come back to leave you as on a cliffhanger with the parking here because it's gonna be a little bit tricky. Okay, so the Lie bracket comes about in the following way mathematically. So we start with something called conjugation in your group. I'm just be some group G and its tangent space TEG, Lie bracket. And so the conjugation operation I'll call psi G. And it just looks like G H G inverse. Okay. So it's a function. You specify the G as a parameter to which psi function you want, but the parameter of that function is just H, an element on G, and so this is a mapping right from G to G, where H gets mapped to GH G inverse. Okay. You ever seen this? It looks it's called conjugation matrix multiplication. Also, this you see in your algebra sometimes. Okay. Notice that if this is a commutative group, if I can change the order of operations, then I can swap the order of H and G, and G inverse is going to cancel an identity, and this is just going to be H. So if this is a commutative group, conjugation is always just the identity function, not very interesting. It's only interesting when the group does not commute. Otherwise, I just get the identity function. Okay. So what we're going to do, because we have a Lie group, I can take the derivative of this mapping, and I'll just put a subscript H to denote we're taking the derivative of the mapping. It's the derivative with respect to its input, which is what not G is really a constant in this whole thing. So DH psi evaluated at H equals the identity. Okay, so we're going to think of this as a tangent space mapping at the identity. Notice that at the identity, if I plug in identity for H identity goes away because it doesn't do anything. I get G inverse, I get identity. So conjugation is a mapping that fixes the identity. For any G, it's the case that the identity maps to itself. So the derivative mapping is going to map any tangent vector at identity to another tangent vector at the identity. It's an identity to identity mapping. So if I give it an input, Y is one of the tangent vectors in my Lie algebra, the tangent space at identity. Think about matrices. I'm going to be very specific to only GLD because I need to do these derivatives in a concrete place that you understand what I'm doing. I can make this more abstract, but it gets really hard. So GH, G inverse are all matrices. I take the derivative with respect to H, evaluated with Y as the perturbation. Matrix multiplication is derivative is just the same thing. It's just taking derivatives with respect to real value multiplication. I can just plug in the Y there. The G's are constant. Okay. If you want to do this kind of like the long way, you do H plus epsilon Y and take derivative of epsilon. You get this. Okay. So the derivative of conjugation in matrix multiplication is also conjugation. It's just now I'm plugging in the tangent vector as the thing I'm conjugating with G. Okay. And now the second trick I'm going to do is I'm gonna take another derivative of this thing. I'm gonna give this a name. I'm gonna call this mapping the big add mapping of Y. It has the same add, the add is for adjoint. And now I'm gonna take the derivative of this mapping with respect to G, the other variable in this little picture. Now do another derivative of this big add business. Again, I have to evaluate it at G equals the identity. And I have to apply it to some tangent vector perturbation of G. Okay, now if I do this, you can see I'm going to do G plus epsilon X, take derivative to epsilon, and I'm going to have to do this with multiplication twice. Right, and what I'm going to get is X, Y, G inverse, but I'm valuing G at identity, so that just goes away. So I get X, Y. And then I'm taking the derivative with respect to little g inverse, and derivative with respect to little g inverse in the x direction is just minus capital X. And again, this g now is identity, and I get minus yx. Okay. I know that's really fast, and because I only have a minute left. The point is that this final answer, derivative of conjugation with respect to H and then with respect to G, with specific perturbation, tangent vector perturbations y and x for A and B respectively, is what we define to be the Lie bracket operation. So the Lie bracket operation in matrix groups in general is xy minus yx for two tangent vectors, two matrices, which I think is tangent vectors in the Lie algebra. The Lie bracket is xy minus yx. You can see very easily that this satisfies anti-commutativity. If I flip y and x, sorry, I left out the minus sign, that gives me the negative. If I go with yx and xy, I've got the negative kind of term there. It's harder to check, but you can check this Jacobi identity that we have over there as well. Bilinearity is pretty obvious because it's just matrix multiplication and subtraction is bilinear. And so this satisfies the rules to be a Lie bracket. Okay. Now, here's now I'm out of time, the kind of punchline of Lie brackets is the following. Lie brackets came about by this commutator, this conjugation operation, which we said is boring if these group elements commute. And infinitesimally, if I'm taking the derivatives of this, if it's boring, I just get 0. If I just get, this is just the identity function, the derivative of a constant function is 0. And you can see that xy minus yx, right, if that's equal to 0, what's happening is that I'm moving in dimensions in my tangent space, which commute with each other algebraically. Okay, so this is what the Lie algebra tells us, is if I'm at identity, and I want to know if I moved in two different dimensions along my Lie group, would those dimensions algebraically commute with each other? And the answer is you can just compute their Lie bracket. If you have matrices, you can do it through this operation. If your Lie bracket equals 0, it means that at least in those two dimensions that you're spanning, you've got a commutative group. The elements are going to commute with each other. If this Lie bracket is anything not equal to 0, then you can tell that you have a lack of commutativity. Okay, I'm out of time, but I'll just I'll start and like take 5 minutes of next time. I'll steal some of Amon's lecture. Don't tell him, but we will do just a really kind of high level understanding of why parallel parking only works because the Lie bracket is non-trivial. If the Lie bracket were equal to 0, if driving and turning commuted with each other, you could never parallel park. But because they do, if you read the notes very carefully, you can convince yourself that you can fit into any tight space as long as you have epsilon extra space. And only because of non-commutativity. Okay, so we'll kind of do that at the very beginning on Thursday. Yeah, thanks.